Thank you for that introduction. So I will be talking about the cosmic birefringence detection or attempts of detection in a map space analysis. Am I gonna be able to change the slide? Yes, okay, perfect. So so the question I'm going to start with is why you would even look at the real or map space. Then I'll be talking about what is cosmic birefringence, cover a lot of the background here for me and Johannes. And then, what could cause cosmic birefringence? How do I detect it or look for it in a map space analysis, some kind of preliminary results, and a summary. So firstly, both kind of why are we using map space and a kind of interesting, I guess the way of thinking about this is that with Cosmoglobe producing these maps, what can you do with some of these maps and why do you need something like Cosmoglobe, which is really good at foreground removal and foreground understanding the foregrounds, as well as giving you all sky results. And in the real space specifically, I think a lot of people will do analysis in the harmonic space because it's this really clean, well understood space. It doesn't have a lot of the issues that you might run into with the map where you have, you can kind of remove the mask, it's not always there, and all these other things. But the map space should be equivalent. So with any good Fourier transform, you should be able to go back and forth between both spaces and get essentially equivalent information. While often one version of a Fourier transform is easier to analyze, it doesn't mean you shouldn't do it in the other space, specifically in this kind of analysis, because the systematics are slightly different often. So by doing both, you can try to understand whether or not your systematics dominated. It's not a perfect check, but it is, I think, a worthwhile check. So hopefully I've convinced you of that. So what is cosmic birefringence, to get to the meat of the matter? So birefringence is often seen in crystals. And what occurs is that when the polarized light passes through the crystal, because of a non-isotropic pattern of the atoms, you get a different bending of the light. Similarly, or probably not similarly, in the universe, the question is, do we see the polarization of the CMB getting bent at different or rotated as it propagates through the universe? So something that would cause cosmic birefringence maybe is a good question. So what we need is some sort of parity violating process, which you only really see in the weak interaction right now. There's a couple of different theories. So a lot of them relate to dark matter and dark energy because, of course, they're some of the most elusive concepts in cosmology right now. So what we're really looking for is something like an ultralight axion, maybe a solar scalar axion-like field. And what it predicts is the rotation of the plane of polarization, and it's proportional to the distance traveled by the wave. So I'm not going to talk too much about these equations. There's a really good review on this topic, and there's lots of reviews on different ultralight axion models and such. But essentially, the main idea I want with these equations is that the phase velocity of the light is affected by the model of your dark matter, dark energy, and it causes the propagation of the two polarizations to be different speeds, I guess you could say, which causes this rotation. And in this equation here, you can kind of see that it's related to the distance traveled. So where eta is the space-time distance, the coupling or the pseudoscalar field is proportional to those. So yeah. So just really quickly here, because I think most people here are experts on this, but with CMB polarization, in map space, you usually have Q and U, which are directional quantities. So they depend where you've measured on the map, but they can be converted into the scalar E and B modes, which don't have a direction anymore. You can see what those look like in the bottom left. Because of the way the CMB polarization is generated through Thompson scattering at the last scattering surface, we should only see E modes. So we should only see these curlless, parity even E modes. And so that's why looking for B modes is interesting, because it would indicate some sort of strange process going on that's would be really exciting to measure. I don't want to spend too much time on this, but I recommend if you're new to the field of cosmology and you want to learn more about polarization, the Polarization Primer by Wayne Hugh and Martin White is really good. So what would cosmic birefringence look like? What's the smoking gun? Here I have the equations that you're probably, so what I have is I have the equations for an observed power spectrum given cosmic birefringence angle of beta. And I want to draw your attention to the bottom two equations here, because for a zero birefringence angle, you expect these to be zero. So in a world where there's no cosmic birefringence, we don't expect any correlations between the TB and the EB. So the E and the B should not be correlated, neither should the intensity or the T modes and the B modes. So Johannes is going to talk more about the harmonic space, but you just kind of need this as background to understand what we're going to be doing in the map space. Okay, so what we want is the transformed Stokes QR and UR parameters when we're looking in map space. So the reason we transform them into the QR and UR is because, as I mentioned previously, the Q and the U have a directional dependence on kind of where they are measured based on the detector and where they are on the sphere. So by using QR and UR, what we're trying to do is we're trying to reorient the spots, the extremum that we're going to be looking at, depending on where they are across the map. So we're looking for stacks on extrema. So, if I look at a spot on the northern hemisphere and I look at a spot on the southern hemisphere, I want to be able to compare those to each other. And so what I need is a method to do that, essentially. And this is how we're going to do it. And when we stack all of the extrema on top of each other, what you get is this profile. I know this looks horrible, like it's a huge amount of equations, but it's going to be okay. We're going to get through it. So W is just the pixel window function and the beam. So it's just a way of kind of deciding how will my peaks look based on the kind of map I have. Similarly with the bias parameters, which I'll talk about next, it's kind of like a maps, how the peaks are going to act in a map. And then we've got our regular second order Bessel functions of the first kind, J2. So just on the bias parameters. So the bias parameters depend on the n side, the window function again. For the E extrema, it also depends on the E mode power spectrum, including noise and mass effects. And in some ways, it's not really a bias because it is calculable. It's more of a statistics of the peaks and trying to understand how the different statistics come into it when you're trying to make these stacks on different extremum to get this measurement. These are kind of what the bias parameters are for different experiments. So PR2 had values that are here, and then these are the values that I calculated for the public release 4, which is N-type. So we've got these Q maps and U maps. We've got extrema. We're going to take all these extrema, we're going to stack them all together. We have a profile for what those stacks should look like, and those profiles depend on the power spectrum. And we know how the power spectrum should change if there's a birefringence. So let's replace the power spectrum that are in these equations right now with the ones that we have predicted given a birefringence signal. And we get this. So we have these stacks with birefringence. So if I make a bunch of stacks on extrema, these are the results that I'm going to get. So important to note is that, again, we have these sign of beta here. So if the birefringence angle is 0, we don't expect any UR in the T or E extrema case. I think maybe I might have missed kind of a key piece here, so I'm just going to quickly cover that. But to make these stacks, we're finding the T and the E extrema from a produced T map, so the intensity map that you would have gotten from this experiment, and an E map that you would produce by going from your QU to E modes. But the full E modes, so not just the power spectrum, but the full ALMs of the system, and you make a map from that. And then you get the hot spots and the cold spots from that map. And then you make the stacks using those locations in the Q and U maps, and then you produce the QR and UR. So I don't know if that was clear, but hopefully that is now. So these profiles, the way they look, essentially this is what this equation looks like. So when this equation is plotted for a N-type style map, essentially, this is what you get. So this is having no noise, no kind of any extra effects, just purely taking the equation and plotting it. On the 2 here is what the stacks would look like kind of in real space. And then if you radially average, this is the plot you get. And you want to often radially average because there can be some weird pixelization effects that can occur kind of close to the center. So getting the radial average kind of smooths a lot of that out, which is good. So as you can see, for a larger birefringence angle, you get larger peaks. So it's easier to observe a large birefringence angle. just previously on the previous slide, because the URs are expected to be 0 for a 0 birefringence angle, they're more constraining than the QR, which are just a slight shift on a large number already. So these are the values that we're going to look at for trying to measure birefringence. This is another kind of simulation. So I've taken a Planck style map. It's noise free, so I haven't added any noise to it, but I have generated it using a birefringence angle of 0.3 degrees. And as you can see, when you do all of the stacking on all the extrema, you get Q signals that look like this. So they're higher signal, but be hard to constrain. And then these kind of quadrupolar patterns in the UMAP are just a pixelization effect. They're not real, and they get averaged out in the in this azimuthal radial profile as well. So, and you can see that the stacking approach mimics what the theory predicts fairly well. So the way that you would actually calculate this birefringence angle beta is as you might expect, you take the theory, you take the data, you compare the theory to the data. You can use just a very simple least squares fit for this kind of analysis, which is nice. And you can also use a small angle approximation for the most part. And you can just compare your theory to your actual measurement, which is the Z hat, and out pops an angle. So it's nice and simple. So just this is a quick kind of breakdown of what we just talked about, because that was a lot, I'm sure. But essentially, the first thing you do is you get the EMAP using Helioptise Anafast. So that's how you make the whole EMAP. Then you can get the total E power spectrum from Nemaster. So that includes then the mask effect. Find the extremas, the hot and the cold spots in the T and the EMAPs. And I'm only including the hot spots that are positive and the cold spots that are negative, but you can change this thresholding if you want to. Calculate the bias parameters for the T and the E spots, which includes the window function beam and other smoothing. You get the UR stacks at each extremum. So you get a UR stack for all the E extrema and a UR for all of the T extrema, and you get a birefringence angle for each of these peaks. And then you can also calculate a final birefringence angle by either averaging the angles that you found kind of across the sky, or comparing the UR to the theory. So there's actually two ways to do this. So cool. Okay, so what did I get? So I did this I'm trying to do this analysis on the Planck results for N-pipe CMB maps. So what you can see here is a histogram found from 100 of the N-pipe end-to-end simulations where I've done this analysis and found a final birefringence angle from the map, and comparing it to the results from the true N-pipe CMB map, which are the vertical lines. And I've also, in this plot, there is the cold spots and the hot spots, just kind of show that they are consistent with each other, as well as kind of the accumulation of all the extrema. And what you can see, and it's kind of more stark in this image here, so I've just removed the hot and the cold spots, so it's just very clear what's being plotted, is that there seems to be a large deviation from a 0 birefringence angle. So the N-pipe end-to-end simulation should not have a birefringence angle, as you can kind of see. And then when you look at the actual N-pipe results, you can see that it's very far off into the fringe of that histogram, which should be really exciting. We should all be going to Sweden. It's very exciting. It's all great, except that it's not. So the thing is, have we detected cosmic birefringence? And the long story short is probably not. So the really important piece about this is that this method does not differentiate between a signal caused by actual cosmic birefringence and one that would be caused by a miscalibration of the polarimeters. So those polarimeters that are looking for light, if they're ever so slightly offset, then you'll get a signal that looks identical to cosmic birefringence. And the Planck miscalibration angle systematic error is 0.28 degrees. So we're well within that range. So we have not detected cosmic birefringence, but it is a cool analysis method, and it is consistent with the results that were obtained in the public release 2 from Planck. So that's good. The results continue to be consistent with each other. And Johannes has had some really interesting, is going to talk a little bit about how we're going about trying to actually separate between these two signals here, the miscalibration angle and the birefringence angle. Just as a quick kind of why is the map space useful in addition kind of thing. So this is what it looks like when I plot the different birefringence angles calculated from across the sky for the T maps. So there's not much signal, or not much structure you can see. So it seems like alpha doesn't seem too area dependent, or sorry, by alpha I mean beta. Beta doesn't seem too area dependent. Similarly, first, there's way more E spots than T spots. There does seem to be a scanning pattern, but you know, it's fine. And again, these are all across the sky, and then you average them to kind of get the final result from the map, because it should average out to 0. If you do different masking, do you get different results? If I mask different areas of the sky to do these averages, do you get different results? This is an interesting question, maybe. And you do, you get a really different result. So that's also, I think, indicative that this result is questionable, because, you know, as you can see, if I, in the T map, the results kind of start to vary quite a bit from what you get in the E map for different kinds of masks. So I think that's also interesting. I haven't done a ton of analysis on this yet, but this is kind of where I'm at right now, is just poking the analysis and trying to see where it flexes. Perfect. Okay, so just to kind of summarize really quickly, is it worth looking for analysis in both harmonic and real space? I think so. Detecting cosmic birefringence would be a smoking gun for really cool physics beyond the standard model. We use the transformed Stokes Q and U maps on stacks ET and E. And preliminary results are consistent with the PR2 results. And we have no detection using this method, at least, of cosmic birefringence yet.